All right, this is 4.1, day 2. So last time if you recall, we talked about the idea that the critical values occur where either the derivative equals 0 or the derivative is undefined. That was the major idea from last time, and it's actually one of the major ideas in the entire course, this idea of where do the critical values happen. So now, if we're looking for an absolute min or an absolute max, so an absolute max or min for a continuous function on a closed interval. So we need a continuous function on a closed interval. We know from the extreme value theorem, as long as we have a continuous function on a closed interval, it will attain its absolute min and max on that interval. So it's either going to be at the endpoints or it's going to be at those critical values. So what we do first is, if you'd like to find an absolute max or min for a continuous function on a closed interval, then first you find those critical values on the open interval AB. And then what you do is you test f at those critical values and f at the endpoints. From there, the largest value from steps 1 and 2 will give you the absolute max, and the smallest will give you the absolute min. So let's use this closed interval method now on an example. So first, find the absolute min and max values of this function on this interval. From -1/2 to 4. Well, we can see that we could draw it like this. If we use Desmos, it will give us something very, very similar. We could type in this and then just put little curly brackets around the domain restrictions. So these are the restrictions for the domain, where you'd like to restrict your inputs. And so what that does is it gives us this pretty picture over here. Okay? So if we would now like to use algebra to find the absolute min and max values of this function, the first thing we would do is we would note that f is a polynomial. That means it's continuous everywhere. That means it's continuous on -1/2 to 4. So since we are continuous on a closed and bounded interval, so by the extreme value theorem, I can find absolute min and absolute max. And here's what I'm going to do. Step 1 is to find my critical values, which are where either the derivative is equal to 0 or the derivative is undefined. So what that means is I'm actually going to take the derivative. So the derivative of my function is just the derivative of this thing. So derivative of x cubed minus 3x squared plus 1. So when I take its derivative, I get 3x squared minus 6x, and that's it. So that's my function. So I now need to figure out where's the derivative equal to 0 and where is that derivative undefined, or where does it not exist? Well, this derivative is undefined nowhere because it's a polynomial. It's going to make sense everywhere. And then when I set the derivative equal to 0, I take my derivative and set it equal to 0. So how do I solve something equal to 0? I factor. So I can pull out a 3x, and I think to myself, 3x times what gives me 3x squared? And the answer is x. And then 3x times what gives me -6x? And the answer is -2. Why do I like that? Because now I have two things that multiply together to get 0. So either this is 0 or this is 0, but that means that x is 0 and x equal to 2 are my only critical values. So step 1 was to find the critical values, and now step 2 is going to be step 2 is going to be to test f of the critical values. You plug back into the original function to find where you're the biggest. Are you the biggest, smallest on the critical values? Are you the biggest or smallest at your endpoints? So maybe I'll write it this way. Maybe I say test f of your critical values. And so that's going to be f of 0 and f of 2. You're also going to test f of your endpoints, and that's going to be, if I can move that down just a little bit over here. And for my endpoints, that's going to be f of -1/2 and f of 4. So if you put in 0 into my original function, go back to my original. So maybe if you'll allow me to do some scratch work up here, if that's okay, I'm going to show you that f of 0 is 0 cubed minus 3 times 0 squared plus 1 is 1. F of 2 is 2 cubed minus 3 times 2 squared plus 1. That's going to be 8 minus 12 plus 1, which should be -3. So that's -3. So far, if that's the only places I were to test, then this would be my absolute max, and this would be my absolute min, right? So this would be my absolute max, and this would be my absolute min if all I checked were my critical values. But I must also check these two endpoints and compare them to how large I was at my critical values. So testing these two endpoints, I think you can pretty clearly see that it's going to turn out that f of -1/2 is going to be 0. We can see that from the picture, but also you would see that with the algebra. And then when you plug in f of 4, you end up getting 17. So absolute max is y is equal to 17 at x is equal to 4. And the absolute minimum value is y is equal to -3. And it happens at, it happens at x is equal to 2. So let's see what happened. Again, just to see overall the flow of things, first, I showed that this thing was continuous on a closed and bounded interval. That means I could use the extreme value theorem that says there will be an absolute min and max on the interval. And so to actually use that, my step 1 was to find the critical values, which are where the derivative is equal to 0 or undefined. Step 2 was to test at the endpoints by plugging my endpoints into f and to plug into the critical values. And so step 3 is really to conclude if we actually need that step. So, I mean, if you want to, you can call this step 3. Boop, boop, boop. So step 3 was just to compare. Boop, boop, yes. So that's step 3. So let's take a second and write that nicely. So I'm going to do a page after, and maybe I'll make it a little bigger. So finding absolute min or max. So step 0 is really show f is continuous on a closed and bounded interval. And then you're ready for step 1, which is to find the critical values, which are where the derivative equals 0 or the derivative is undefined. Step 2 then is to evaluate or plug in f of the endpoints, find out what you get, and f of the critical values. Then step 3 is to compare. So compare what you got. Compare what you got from the endpoints and the critical values. So largest from step 2 is absolute max. Wow. Smallest is the absolute min. So that's how you find an absolute min or max. Well, you would need to show that your function is continuous on a closed and bounded interval, find critical values, evaluate f of the endpoints and f of the critical values, and then compare what you got in step 2, where the largest from step 2 is your absolute maximum, and your smallest is your absolute minimum. I would assume by the next time I see you, you can describe this procedure to someone. If they ask, how do you find an absolute min or max? Describing this process would be very important. All right, let's now look at example 9. So if we're going to look at example 9, it says use a graphing device to estimate the absolute min and max of this function on this interval. Well, what I can do is I can come over here to Desmos, and I can put in x minus 2 sine x. Then I use these curly brackets, and if you put in those curly brackets, which you can find down here by clicking on ABC in the bottom left-hand corner, if you use those curly brackets, which are right here, you would be able to put in a domain restriction. So I do 0 less than or equal to x less than or equal to 2 pi, and it ends up giving me just a restricted version of what this picture looks like. And when you click on the graph, it's beautiful. It automatically shows you the value at the endpoints. Yeah, and it shows you the value of the min and the max. And then it also shows you any zeros. So this is pretty nice. So the values that we're looking for are actually pi over 3 and 5 pi over 3 are where that absolute min and absolute max occur. Let's see if we can find it using algebra. So let's use calculus to find the exact minimum and maximum. So maybe I do step 0 is that f is continuous on 0 to 2 pi because it's the sum of a polynomial and trig function. So it's nice. This thing is continuous everywhere, and so is this. So it is a sum of those two sorts of things, so it's good. It's actually a linear combination, but whatever. So step number 1 is to find the critical values. And that's where the derivative equals 0 or that derivative is undefined. We take the derivative. It's going to be the derivative of this function. Boop, boop. And I think you can very quickly see that that gives us 1 minus 2 cosine x. So I can either find out where's that thing equal to 0 or where is that thing undefined. Well, it's going to be undefined nowhere. Because again, because sum of polynomial and trig function, it's going to be nice everywhere on its domain. And then finding out where it's equal to 0, I just take this thing. Oh, I did the wrong thing. Take this 1 minus 2 cosine of x and set it equal to 0. 1 minus 2 cosine of x, set it equal to 0. So we get 2 cosine x is equal to 1. In other words, 1/2 is equal to the cosine of x. So if I'm only looking on one rotation, then I'm really looking at trig hand. So I find out where on my trig hand, 1, 2, 3, 4, 5. So I'm looking for when would I get cosine is on top and sine is on bottom. So when would I get 1 finger over 2? Well, I must have put down this finger to get 1 over 2. So that means it would be pi over 3, right? So when I'm looking at my circle, that means that the x-coordinate, since cosine is x, that means it's going to be over here at pi over 3. But I think you see another place where that x-coordinate will also be pi over 3. It's going to be right here. Yes. Oh, I'm sorry. The x-coordinate is 1/2 when I open up pi over 3. So I should make that very clear. And what this is pi over 3 is the angle I open up to get an x of 1/2. And then from your trig hand, you know that the associated y is the square root of 3 over 2. That means there's a point very similar to it in the fourth quadrant where x is 1/2 and the y-coordinate is negative square root of 3 over 2. So that's my cosine sine in that quadrant. So if I want all the places where my x is 1/2, it's going to be pi over 3, or if we went back, negative pi over 3, but that would be the same as 5 pi's over 3. We went around and stopped. So that means that x is equal to pi over 3 or 5 pi over 3. Right? So those are my only critical values. So now what I'm ready to do, if you'll give me a second, let me make a little space down here. Is that as big as this thing goes? No. Let me use some whiteout to give myself some more space. There are other ways to do this, but this is easiest at the moment. Okay, boom, boom, boom. So if I just did step 1, now I'm ready for step 2, which is to evaluate f of the endpoints and f of the critical values. So f of the critical values would just mean that I take my original function, which was x minus 2 sine. And so if I, at pi over 3, I guess I'm going to get pi over 3 minus 2 sine of pi over 3. But I know that the sine of pi over 3 is the square root of 3 over 2. So this is going to end up being pi over 3 minus 2 square root of 3 over 2. So it's going to be pi over 3 minus square root of 3. At 5 pi over 3, I'm going to get 5 pi's over 3 minus 2 times negative the square root of 3 over 2. Is that right? Sine's going to be, let's see, I'm down. Yeah, sine's going to be negative. So it's negative square root of 3 over 2. Make sure that's right. So I'm looking for sine, which is down here. Cosine, sine, cosine, sine. Yeah, that's right. And so then those add together, and I get 5 pi over 3 plus the square root of 3. So definitely this one is winning for the biggest so far, and this one is winning for the smallest, right? Then I guess I need to find, I've done all that so far. That's f of the critical values. So then if you let me come over here and do f of the endpoints, I'm going to do f at 0 and f at 2 pi. So f at 0, f at 0 is going to be 0 minus 2 times the sine of 0, which is going to be 0. And then if I do f of 2 pi, it's going to be 2 pi minus 2 sine of 2 pi. That sine of 2 pi is also going to be 0. So it's just going to be 2 pi. So now I have to compare 0, pi over 2, pi over 3 minus 3, and 5 pi over 3 plus 3. So I think it's pretty clear. Should it be really clear that this is close to 2 pi, but I add even more? So this is going to be bigger than this guy or this guy, right? So this is not going to win for the biggest. I think this one's winning so far. And then this pi over 3 is really, since pi is about 3, this is about 3 over 3, which is 1, minus the square root of 3, which is bigger than 1. My guess is that this is negative. So this is going to win for the smallest, and this is going to win for the largest. So I think the smallest is at pi over 3, and the largest is at 5 pi over 3. And so when we look at our picture, yes, the smallest is pi over 3, and the largest is 5 pi over 3. Cool. So if I didn't have a calculator, I would still be able to say that this is negative, and this is the absolute minimum. And this thing turns out to be the absolute maximum of our part, step 3, which is to compare these values that we got from plugging in the endpoints into the original function and plugging the critical values into the original function. All right? Great work. So I would go back here and show you one more time the common mistake. Caution. So how do I find the absolute min and max of a function on an interval? First, step 0 is show me that it's continuous on a closed and bounded interval. So extreme value theorem applies. That's really what we're trying to say, is that we can find an absolute min or max, that we don't have to waste our time doing these if this is not true. Or we have to use another tool. Step 1 is to find your critical values. Step 2 is to evaluate f of the endpoints and f of the critical values. Caution. So what's the common mistake that people use? Plug into original function, not f prime. That is the most common mistake that people make in this process, is you plug into f to find out what is the biggest output of f, not f prime. And then step 3 is just to compare what you get in this process, where the largest is the absolute max and the smallest is the absolute min. Yeah. All right. So that's it. Have a great rest of your day, and I'll talk to you soon.